you teach it at 1:30, do you have like a problem with it?
Honestly, a little bit. Yeah. But not in my grad class. Like my RL class is usually pretty high attendance. But yeah, we'll see. Okay, exciting. Let's talk about some more imitation learning, and we will get into some reinforcement learning. So, just a little recap before we get started. We were talking about this algorithm called behavior cloning, right? And so behavior cloning is this maximum likelihood algorithm. We're trying to maximize the likelihood of expert actions at expert states. So we take our state action tuples, we jumble them up. We treat this as a regression problem going from X to Y. Then we just, if it's discrete, we use a cross entropy loss. If it's continuous, use a mean squared error loss, right? And then you just train with supervised learning. Model you train with supervised learning. And then you can just deploy the model sequentially. So you trained it non-sequentially and you deploy it sequentially. And we said that that makes training easy, but it gives you a problem at deployment that your training and test distributions are not the same. And so your training distribution is pretending that it's a non-sequential problem, whereas your testing distribution is definitely sequential, right? Because you have to run it in the world. And so that's what led to this compounding error problem. You make a little mistake, it becomes a bigger mistake, a bigger mistake, a bigger mistake, and so on. And so the primary issue is that the train and test distributions don't match in behavior cloning. We proposed a fix to it, which is trying to make the training distribution closer to the rollout distribution, the distribution you get when running the policy in the world. And so this is this idea called Dagger. And Dagger is very simple, right? We said we're just going to keep running our policy. We're going to start by training our model on the current training data. We're going to then run our policy in the world. It's going to make some mistakes, get off track. On all of those things where it went off track, you're going to have a human provide the optimal actions, right? And then you're going to get an updated data set. You're going to aggregate that data set. You're going to repeat, right? And so if you remember graphically, like we said, this was our optimal trajectory. We like deviated from it, right? What Dagger is going to do is going to go to all of these states, provide a label, right? You're going to add those labels back into your training data set, and you're going to repeat. And so the idea is that essentially you're just going to keep whack-a-moling your errors until your training data set covers all the places where you get by making, because of those mistakes that you made, right? And so you can show provably that Dagger will converge to a good policy, and behavior cloning you can show has error, which is quadratic in the horizon. So the longer the horizon is, it gets quadratically worse in performance, whereas Dagger is only linear. That's how you get a whole factor of improvement. So Dagger is an interesting algorithm, but if we look at this algorithm, there's two issues, right? The first is that you have to run pi theta in the world. The second is that if you ask a human to label things, right? And we have to ask a human to label things post hoc on these observations, which is kind of awkward. It's like you had a car driving, and after it drove kind of wrong, you like showed it pictures of where it was and said, "What would you do?" It's not really how you actually provide data, right? So we studied two kinds of fixes to this. The first one is this algorithm DART, and all it says is that add a little bit of noise to data collection and have the human provide you corrective data in a tube around the optimal. And then we covered a second idea, which is this algorithm we came up with called CCIL, which is saying you don't want to have a human involved for these corrective labels. You can just use a dynamics model, a model that you trained to predict how the world works, right? A world model, and use it to figure out what data goes back to the. So you just have to be careful about staying close to the training data. But the general idea, like the high level idea here is that this is using a human to correct. This is using a model to correct. Right? Does that make sense? Everyone with me? Okay, so that is what we covered last time, right? So imitation learning, simple way to do it is behavior cloning. And there's some problems with behavior cloning, right? We covered some fixes to them, but behavior cloning, it's not all doom and gloom. It actually works unreasonably well, right? We saw a lot of those videos online, which is largely behavior cloning, and it can work well when you make the right design decision. But we'll cover a second issue, which is a little different, right? And so sometimes what you'll find is that even if you have a really large model, you'll find that you're underfitting the data, right? And so what you'll see here is that like as I said, behavior cloning has a objective which is quadratic. So like the error that you have is quadratic in horizon, but it depends on this epsilon, which is like what is your training error? So epsilon is like how well are you fitting your training distribution? And what you'll find in imitation learning sometimes is that you will um, you will end up overfitting, underfitting, which means that even if you make your model bigger and bigger and bigger, like in supervised learning, it tends to just like get better and better and better until some point. But in imitation learning, even if you make your parameters bigger, your model doesn't underfit less, which is kind of counterintuitive, right? Like what we learn in machine learning is you have an underfitting problem, make your model bigger, 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 right? And so I think we need to look a little deeper to what's going on. So the fundamental problem that's different in imitation learning is that you have like a policy expressivity problem. And so what I mean by that is that if you think of what a policy is, right, it is a neural net which is parameterizing a probability distribution, right? And so it is not just a single number, it is a probability distribution, right? And so you have different types of probability distributions that your policy could be. Let's say you could have like a categorical distribution, which means that your neural net takes in state and outputs like, a vector over actions, a normalized vector over action probabilities, which is categorical, right? You could have a Gaussian, which is your state takes in a neural net. The neural net has two heads, one which is for the mean, one which is for the covariance, right? And that gives you a Gaussian. You could have something which is a diffusion policy, which takes in S, gives you something which looks like a score function, like a denoising function, and that gives you a diffusion policy. And so each of these are different policy classes, right? And so when I say something is pi theta, it's an abstract notion, but when you go to write it in code, like you have to choose a policy class. You have to choose like a probability distribution. If you wanted to do maximizing log pi theta of A star given S star, you need to like choose a family of probabilities to do so, right? And what you can show is that like the cross entropy error that you use um for most discrete problems is kind of using is maximum likelihood on a categorical distribution. And you can show that the mean squared error, which is what you use for most continuous distributions, is a maximum likelihood on a Gaussian, right? And so in general, when you think of the expressivity of a policy, it is the combination of like how big is your neural net, how powerful is your neural net, and how expressive is your probability distribution. So what do I mean by expressive? Like, what does it mean for two distributions to be differently expressive? Yeah.
I guess we have like several data like concrete expenses to like the perfect way.
Yeah, exactly. So imagine that you had like data that looks like that. Like a Gaussian is going to give you something like this. That's the best fit that you can have, right? Whereas like what a categorical could give you is something that looks like this, but it is like bound to whatever discretization error you have. And something like a diffusion policy or diffusion model could give you something closer to fit, but it has its own cons, right? So, um, but the important problem here is that if you have, let's say, this example where you have a car or a drone going at an obstacle, and sometimes people give you demonstrations to the left, sometimes people give you demonstrations to the right. And so you have like a naturally bimodal distribution, right? So your action distribution at this state looks like this, right? And let's say I trained imitation learning with mean squared error, right? So mean squared error means I'm going to like try and maximize the likelihood of a Gaussian. And so if I'm going to try and fit a Gaussian to this, what's going to happen? It's going to get, this guy, right? And so one important thing is this objective is often what you'd call mode covering. So when you say mode covering, like you really don't want to not have any likelihood in any of the modes, right? So the way to think about it is if there's something that has likelihood here, you really don't want it to be low likelihood under your policy, right? So your Gaussian is never, it's going to try and cover as many of the modes as possible. And so in this example, if I train my model, I'm going to go like right into the um, right into the tree or whatever. But the important thing here is that it's it's because my policy class wasn't expressive enough. If I had a more expressive policy class, then I would like pick left or right. I wouldn't have the same underfitting problem. But if you just train with mean squared error, like most people did, then you have a multimodality problem. And if you look at most human data, it's naturally multimodal, right? Like even us, who you demonstrate things 10 times, you'll demonstrate things different ways. Sometimes you go left, sometimes you go right, sometimes you go up, sometimes you go down. Different people do things differently. And so if I have a huge data set of like, you know, um, 10,000 road miles on Waymo or something, like some people will choose to overtake this way, some people will choose to overtake that way. So like generally it's human data is naturally very multimodal. And so you want policies that are expressive enough to capture like not just bimodal, but like something like that. Okay. So um, the big advancement in the last few years has been to like instantiate methods that are like way more expressive than these Gaussians, right? And so um, there's a bunch of different ways to do this. But the ones that we're going to kind of think about are these ones. Right, so the first is a mixture of Gaussians, the second is latent variable models, the third is autoregressive models, and the fourth is diffusion. So essentially the commonality here is all of these are essentially what you'd call generative models. It's like generative AI, right? It's models that people used for, let's say, image generation or text generation, right? And you're kind of applying the same methods to robotics for action generation. And so, for instance, like text is very naturally multimodal. You have a prompt and you have like many, many different completions of that prompt. And so you definitely don't want a Gaussian for text, right? And so similarly for actions, we're going to try and use some of these more expressive distributions. Okay, so the first one, the most obvious one, which is to go from a Gaussian to a mixture of Gaussians, right? And so when you say a mixture of Gaussians, you'll say that the policy can be represented as a mixture of, k different Gaussians, each which has a separate mean and covariance, and then a weight vector, which sums up to one, right? So if you just integrate this thing, it's a proper probability distribution because it sums up to one, but it can represent things that are more complicated because it can represent things as like combinations of many Gaussians. Why is this not the catch-all solution for everything, though? You're restricted to some k Gaussians, and if you really want to capture things that are really complicated, the number of Gaussians you have will explode. And you also don't know how many Gaussians you want to choose. So um, it can be hard to be performant, but it's better than a Gaussian. The next class of models that are often used are these things called autoregressive discretization. And these are like what you do in your transformers and so on, right? And so the idea behind autoregressive discretization is neat. So imagine that you have like a k-dimensional action space, okay? So you have like let's say like three-dimensional action space, A0, A1, A2. Now, what I'm gonna if I was to like just like think about binning this action space, right? Which means I want to convert this continuous action space into a discrete action space so I can build a table around it, right? If you remember our discussions during state estimation, right? Like discretization is hard because you have exponentially large number of bins, right? So imagine you had three-dimensional action space, you had joint one, joint two, joint three. And then you have like, let's say, 100 bins for this, 100 bins for this, and 100 bins for this. The total number of bins is 100 to the 3, right? And that is huge, which means that my table is now like my neural net has to output 100 to the 3-dimensional vector. And you don't want to do that. And so the idea behind autoregressive discretization is simple. It says that what I'm going to do is I'm going to bin dimension 1. So I'm only going to have 100-dimensional output. And then I'm going to like feed the output of dimension 1 into the prediction for dimension 2. And I'm going to feed the output of dimension 2 into the prediction for dimension 3. Right? And so you can kind of use the chain rule of probability, which says that if I have A0, A1, A2, I can write this as A0 times A1 given A0 times A2 given A1 and A0. Right? This is the fundamental chain rule of probability. And so what that suggests is that you can bin them independently. And so the number of things that you have to produce is not 100 to the power 3, it's 100 times 3, which is much more manageable, right? And so what you'll typically do is you'll just have like, when you say autoregressive, that means the output of the model is going back into itself, right? And so you're going to like produce a vector for A0, sample from it, stick it back into the model to produce A1, sample from it, stick it back into the model to produce A2. And you'll represent it as a transformer or an LSTM or something. But it makes your like high dimensional things a lot more scalable. Does that make sense? So essentially what you're trying to do is you're trying to factorize the action space per dimension. And you're trying to not predict 100 to the 3 by discretizing blindly. You're trying to like predict one thing at a time, feed it back in, predict one thing at a time, feed it back. Okay, so that seems reasonable. Why is it again not? What are the cons of doing that? What might go wrong? One thing that's naturally a question is I have three, like the chain rule is fundamentally underspecified. So I could break it up this way, but I could also break it up as P of A2 times P of A1 given A2 times P of A0 given A1 and A2, right? So you can have many orders to the chain rule, like which order should I choose? The other thing is because you're going dimension by dimension, if you scale to something that is really, really high dimensional, like the number of times you have to go forward through your model scales with dimension, right? So if I like imagine I had some like huge LLM, some way of producing the action, then I need to go through that forward pass like D times if D is my action space. And that gets computationally expensive. So the challenge with autoregressive models is that they can get really computationally expensive. Okay? The last one that has become more popular recently is this idea of diffusion models. Are folks familiar with diffusion models? Yes? Ish? Okay, so the idea of a diffusion model is interesting. The diffusion model, like literature, kind of started with actually one of my lab mates in grad school, but the the fundamental premise is if you took an image and you like started from an image and added noise, till it become like random Gaussian noise, right? So imagine you took an image and blurred it, till it became noise. And then if you learn to unblur it, then you understand the fundamental process of generating images, because if you can go from noise to images, you kind of understand the manifold of images, right? And so the idea of diffusion models is generally to take data, add noise, till you get to like random Gaussian noise, and then learn how to reverse the process. And so if you can reverse the process, then you can generate new images by sampling new noise and then denoising, right? And so that's the way that like if you use Gemini, Nano Banana, if you use like Stable Diffusion, Midjourney, like all of them use these diffusion models to generate images. But mechanistically, you can kind of think of it as like you have some X, you start from X, you start adding noise till you get to like XT, which is all noise, right? And then you learn to like reverse it. And you add like really controlled, you have to add a particular form of controlled noise. And if you add a particular form of controlled noise, there's a easy way to like learn the reverse process. Right? And so the cool part about diffusion models is that they can represent like really, really complex distributions. So if you have a distribution which is like this, something that is really nasty, it is much easier to represent it with a diffusion model than it is to represent it with, a mixture of Gaussians or a table or something like that. The other nice thing is that it scales well to high dimensions, right? But the important thing is that in a diffusion model, you are not going to generate the answer in one shot. You're not going to say state goes in and action comes out. What happens is you start from a state, you take an initial guess, right? Or let's we haven't even gone to states yet. Let's just say we're like generating images, right? You're going to start from an initial guess of my initial guess of an image was X naught. Then I'm going to denoise, I'm going to denoise, I'm going to denoise for K steps. And then that's my final answer. Right? And so it's like fundamentally an iterative process. So you can kind of think of the diffusion model as like an iterative process that allows you to express really complicated distributions. And so for robot data on like high dimensional, like let's say bimanual manipulators on or humanoids, that's been found to be super duper effective. And the con here is that diffusion models don't give you likelihoods. So like for instance, you wanted to do, log pi theta A star given S star. What diffusion models don't give you is they don't give you a closed form likelihood. Right? So when I say closed form likelihood, I mean like if you look at like something like a Gaussian, right? Um, you'll have something like this. That's like the likelihood of a Gaussian. It's closed form. Like I can always compute what the probability under a Gaussian is, but it's really hard to compute what the probability under a diffusion model is. And so that makes things um, like for supervised learning, it's fine, but it makes things like reinforcement learning with those models harder. And we'll cover that in a sec. But it's not a silver bullet. And then the other thing is it can be slow because you're like doing this iterative process. You're like doing 50, 100 steps of iterative computation. It can be slow to generate things. So if you want robots that are going super fast, it can be a problem. But it's So I definitely gave you a very abridged description of this. I'm happy to send more resources about it, but diffusion models are cool. Okay, so the fundamental idea to convey here is that compounding error is not the only problem in imitation learning. Multimodality is a second problem, but we have lots of methods to deal with it by using ideas from generative modeling. How do people feel about this, right? So first idea, compounding error, fix it with corrections. Second idea, you have complicated multimodal data, just make your model a more expressive model. And that helps. Any questions? Okay. I'm going to rush through this, but some challenges here is generalization. But you can have these dictionary policies work on the training set, but you can have failures like this inspection, RLAP. But you can also see that like some things we want. I want you to like, point to a particular image, and it like struggles with generalizing to new instructions and new semantics. And so a paradigm that lots of folks have been building on recently is this idea of vision language action models, or VLAs. And the idea behind VLAs is to treat the robotics problem as a vision language problem. Right? So say that like, vision language problem largely is treated as a captioning problem. You have an image in and a text caption out. Right? And so what a lot of the vision language action modeling literature does is to like force feed a robotics problem into text an image captioning problem. So the caption is the actions that come out, and the input is the image that goes into the robot. And so you can kind of think of essentially all that a VLA model is just imitation learning, where you use a vision language model as your policy class. And you're going to say, I'm going to feed in my image, thing that the robot sees, and then I'm going to convert my action into text. If I can convert my action into text, I just make my VLM predict that text. Some people do prediction of text. Some people put like a few more layers of neural net at the end to predict continuous actions. But the general idea is to like leverage a lot of the pre-training from vision language models, and that's what gives you generalization to new embodiments, to new objects, to new tasks, to new instructions. And so uh, there's a fun video. Some folks at Pi where they do laundry, they fold clothes, and what else do they do? They make some coffee, they make boxes, they bust tables. And the cool stuff is that it's the same model. It's trained across lots of different embodiments. Just by doing this paradigm of converting the robotics problem into a vision language problem. Okay, so that's the first thing. If you're interested, go read up about it. It's kind of a big burgeoning space right now. The second problem is data collection, right? So Data collection is fundamental to imitation learning, and in some cases it's easier than others, right? So for driving, it's easy because you're driving, but let's say you have like a really high precision robot. So here's like a bimanual robot where you're trying to like, build little watches and here's like a robot where you're teleoperating it through VR. But often these things are really hard to control because especially on the left, it's a puppeting device. So what happens is you move the two leader arms and the follower arms follow exactly where you're moving. But you have to like mirror yourself to think of where the arms are moving. And it's just like, we have some in the lab. If y'all ever come by, check it out. It's just like a little hard to get it right. And it's hard to do it at high throughput. It's hard to generate lots and lots of data. Um, a fun anecdote my advisor was telling me is that they have like a big group of teleoperators at their company, and they found that like people who are bakers are the best teleoperators. And so like if you're dexterous at other things, then you often are dexterous at teleoperation, but it's a bit of an art. And that kind of limits your data collection speed. And it's not definitely not at the speed that people are doing stuff. So one area that has been really interesting has been how people have tried to construct new interfaces to collect data. This is one called the Universal Manipulation Interface, or the UMI. And essentially what they do is they have like this little glove type thing, the thing on the left, and they have a person just hold the glove and do stuff, right? Like they're saying that a human just holds the glove and you have like a wrist camera. The wrist camera is like seeing where you're going. And the human just does stuff by themselves. There's no teleoperation, there's no controlling a robot. The human just does stuff and records stuff on the camera. And then you like make the robot wear the same gloves. And so the point is you kill the embodiment shift, but you're like collecting data at the speed of humans minus some epsilon. And so that kind of allows you to scale data collection a lot better. And so many of the results we showed earlier collect data with this kind of interface, and that tends to work really well. And so some of the examples we had showed earlier in the class are also based on this kind of like handheld gripper interface. And so people have been thinking about like using gloves and sensorizing people and using exoskeletons and like lots of interesting ways of collecting data faster and more accurate. Okay, so to conclude imitation learning, you'll see a lot of stuff online. A lot of it is imitation learning. A lot of it's going to tell you the world is solved. It's certainly not solved. It can be unreasonably effective. But there's fundamental challenges of compounding error and multimodality, which make it hard to be reliable all the time. It doesn't always generalize, and it can be really expensive in terms of data collection. So if you want to collect 10,000 hours of data, that could be tens of millions of dollars. Questions before we move on from imitation learning? Or, how do you feel about imitation learning? Generally reasonable? The other thing about imitation learning is if you're interested, it's super easy to try. Just there's this library called the Robot from Hugging Face, and it lets you like get up and running in like 2 hours. So give it a try. Okay, ready to go to reinforcement learning? Cool. Alrighty, so we at the start of our learning module, we talked about different ways of doing decision making, right? So we started off with imitation learning, and we said, hey, we're going to at least cover one type of imitation learning, which is behavior cloning. We covered some issues with it. We covered some fixes, right? But today we're going to think about a different type of decision making, which is model-free reinforcement learning. So what is model-free reinforcement learning? Here's an example of model-free reinforcement learning. There's some milk on this plate here. We have a bunch of dogs and our puppies, and they're trying to find a way to the milk through this like contraption. And this is surprisingly reminiscent of how RL algorithms explore. But essentially, they're trying a bunch of stuff, and eventually someone's going to find a way there, and then the agent starts doing it more and more and more. But what I'm trying to get at is it's essentially a process of trial and error. It's like a formalization of the process of trial and error. You try stuff, you see which stuff was good, which stuff was bad. You do more of the good stuff, you do less of bad stuff. That's the fundamental intuition behind model-free RL. Okay, so let's try to formalize this. So if you remember from earlier, our goal in model free RL is to maximize the expected sum of rewards when you're sampling trajectories under your policy by theta, right? So I'm going to use some trajectory shorthand. So I'm going to say that our goal is to find theta such that we're maximizing. If I was sampling trajectories from p theta tau, and I'm denoting the sum of rewards in a trajectory as r tau, I want to maximize the expected sum of returns under my policy, right? So I want to maximize this objective with expected theta. Okay, that's the RL objective. Okay, so how do I optimize it? Don't look at the title. But if I was to optimize this, you're trying to maximize this reward. How would I do it? I guess the tricky thing is I gave you the answer on the slide. So we're going to do gradient descent, okay? So we're going to do gradient descent. So typically when you have a function, imagine you had a function, right? You want to maximize it. You want to find a local optimum. You can do gradient descent. You can start from a guess. You can take a step. You can take a step. You can take a step. You can take a step until you reach an optimum, right? And like it's a way of optimizing functions, at least to local optima. And so we are going to try and apply the same idea of gradient descent to this problem. Okay, so what we're going to try and do is we're going to take this problem, right? And we're going to try and do gradient descent on it. Yeah. P theta is the probability of sampling a trajectory when you're running your policy pi theta. Right? So it's like we'll unpack it in 2 slides, but basically you can think of it as like if I was running my policy pi theta in my dynamics model P of S prime given SA, and I like get a trajectory, it is the probability that when I run pi theta, I get some trajectory tau.
Is it just expanding the expectation?
Yeah, yeah, it's that sequential chain of expanding the expectation. So okay, but if I think about this problem, grad theta of p theta tau of r tau, there's a little bit of subtlety here. So if you let's think of a supervised learning problem like we did um, in behavior cloning, right? So what we said is we were going to do x comma y from D. We're going to maximize the likelihood of y given x, right? And again, we had a similar maximum likelihood problem, right? But these are not the same, and it's very important why they're not the same. The importance is that like in the reinforcement learning problem, the thing that you're taking the expectation with respect to, right? The thing that you're like the probability distribution is parameterized by theta. So this thing has theta in it. Whereas in supervised learning, this thing does not have theta in it. Okay. So, and the way to think about that is like in reinforcement learning, your policy is controlling your data distribution. In imitation learning, your policy is not controlling your data distribution, right? And so the important thing here is that like when you have an expectation, the thing you're taking expectation with respect to is your optimization variable, whereas in imitation learning, it is not. So when it's not, you can take the gradient all the way inside. And so you can often have, let's say you had maybe like in abstract form, right? Look at the difference between these two optimization problems. One of them has theta in the expectation, or theta has the expectation probability. The other one has theta inside the expectation, but not in the probability. So this is supervised learning. This is imitation learning. This is maximum likelihood. And so the important thing is that this is not dependent on data. The data does not depend on data. Whereas here, the data does depend on data. Right? The probability distribution does depend on data. That's going to lead to a totally different algorithm. So it's like super small looking as a difference, but it does fundamentally matter. And the way to intuitively think about it is that in reinforcement learning, you're trying to control the data generating distribution. Whereas in imitation learning or supervised learning, the data distribution is coming from an expert. You have no control over it. You only have control over your predictions. The two different problems. Right? And so in this problem, like the easy way to think about it is if I have an integral, oh shit. Okay, so if I have an integral, like whenever I have the expectation of, some, say, p of x, f of x, remember that you can always write it as the integral p of x, f of x dx, right? That's the definition of an expectation. And so on the left, we can write it as integral g of x, f theta of x, dx, gradient, right? I can move this gradient inside into here because this is a constant with respect to theta. So I will get integral g of x, grad theta, f theta of x. Okay. And now this is a probability distribution, so I can rewrite this whole thing as essentially the expectation g of x, grad theta, f theta of x. Okay. So you see that I'm able to move my gradient all the way inside. And so the way you implement this, you just take PyTorch, just like add up a bunch of losses, and you like average them and you're good. And so that's what typical supervised learning would do. And what we're going to have trouble with in reinforcement learning is that the thing you're taking expectation with respect to has theta in it. Right? So we're going to try and work out how to compute a tractable gradient here. So remember, there you can take the gradient inside. Here it's hard to take the gradient inside. Okay. So this kind of conceptually makes sense. Conceptually, we're saying in reinforcement learning, you are sampling under the probability distribution of the policy, and you're trying to find the policy that gets the most rewards. In imitation learning, someone gives you a data set, you're trying to maximize your prediction accuracy. It's like a different problem. Okay, so this is going to be our problem. J theta is the expected sum of rewards. Right? So it's saying that when I act according to a policy by theta, this is the likelihood of sampling a trajectory. This is the reward of any trajectory. So I'm going to take the expectation p theta tau of r tau can always be written as an integral. Yeah. Okay, so now what we're going to do is we're going to try and compute the gradient of this objective. So we're going to try and take the gradient of this objective. And again, we can move the gradient inside the integral. R is a constant with respect to theta, right? The only thing that depends on theta is the first term, right? And so if the first term depends on theta, we can write this as grad theta p theta tau, r tau, p tau, right? So it's a valid objective. But the important thing is it is no longer a probability, it's no longer an expectation. So like whenever you have an expectation, you want to have p of x, f of x dx, right? So you want this thing to be a probability distribution, which means that it is positive and it integrates to 1. And this thing is the thing you're integrating, right? This thing is the thing you're taking the expectation of. So if I ever have expectation p of f, I can write it this way, right? Now this thing is no longer a probability distribution, or this thing is no longer an expectation because this thing is no longer a probability distribution. Like p theta is a probability distribution, but grad p theta is not a probability distribution, right? And so the important thing here is that I can't express this as an expectation. And if I cannot express it as an expectation, I find it really hard to implement it by touch. And so what we're going to, or I find it hard to implement with samples. So what I'm going to try and do is I'm going to try and convert this into something that looks like an expectation. Okay. So when I say something that looks like an expectation, it's going to be some p, which is a true probability distribution, multiplied by some f, right? Okay, so there's one trick in model free RL, which is what we're going to use to try and convert this into an expectation. So remember, an expectation is a probability distribution times some function. So this has to be probability. This can be anything, right? So what might I do to this object? What might I do to this expression to make it an expectation? Ideas? Almost. So what we're going to do is we're just actually going to multiply and divide by p theta tau. So it's not by the sum, because sum is hard to compute, but we're just going to multiply and divide p theta tau. Right? And so This seems like it shouldn't do anything, right? But what we're going to do is we're going to multiply and divide, and then we are going to like group this term together and like, or rather, um, kind of like group these terms together, right? So in the form of our expectation, this thing is a probability distribution, and this thing is an F, right? So it becomes an expectation because you multiplied and divided and you rearrange the terms a little bit, okay? Um, but the cool thing is, you all remember the chain rule of calculus, right? If you look at the chain rule of calculus, if I compute this thing, right? What is grad theta log p theta tau by chain rule? So remember, grad theta is basically d over d theta of log p theta tau. Okay. So what is the gradient of log? 1 over, right? So gradient of log, you can write this by a chain rule as gradient log p theta tau by p theta tau times gradient p theta tau theta, right? Now remember, the gradient of log is 1 over, right? And so this thing becomes, if I look at the gradient of log p theta tau, it becomes 1 over p theta tau. And remember, this thing is nothing but grad theta p theta tau, right? And so if I look at this expression, if I look at this expression, it's kind of the same, this expression, right? So this expression, grad theta p theta tau divided by p theta tau is exactly the same as grad theta of log p theta tau. Make sense? So all we did is we used the chain rule here. We multiplied and divided. We regrouped the terms, and then we noticed that the grad theta log p theta tau is exactly equal to this and this term put together. Okay. Takes a little while to internalize, but think of it as like we started with the expectation. We expanded we expanded the expectation as an integral. We moved the gradient of that integral, we moved the gradient to be inside that integral. We multiplied and divided by p theta tau, right? So nothing changed. We just multiplied and divided, right? And then we just grouped these terms together. We grouped these terms together, and we said by chain rule, this is just the gradient of log p theta tau. Okay. And so when you put that together, you get an expression that looks like this. Right? So all that we did is we said this thing becomes log p theta tau. And now this thing starts looking a lot more like an expectation. Right? So this thing starts looking a lot more like an expectation. This is our P, this is our F, right? And so if you look at this objective, you can write it as now as an expectation under P theta tau of grad log P theta tau R tau. Okay. So all we really did is we took the gradient, we did some algebraic manipulation, and we converted it back into an expectation. So the original objective was an expectation, and the gradient is also an expectation. And the reason you want an expectation is if you remember Monte Carlo sampling from like particle filters, whenever you have an expectation, you can approximate it with samples, right? And so when you have an integral, it's really hard to deal with because you have to like sum up over everything. Whenever you have an expectation, if I have samples from p theta tau, I can approximate this expectation. So what I've done is I've converted the gradient of this thing, which was originally this nasty looking integral thing, which I don't want to deal with, to something that is an expectation. So as long as I can draw samples from p theta tau, I can compute an approximation to the gradient. Okay. So questions. I know that was a lot. Sorry. Okay. Thoughts, questions? Are we totally lost? Should I restart? That's fine for me. It's a game of chicken who can be silent for longer. But let's recap, right? So our goal is to maximize the expected sum of rewards, which means when I draw trajectories from my policy, right, I want those trajectories to be as, on average, as high reward as possible. Right? That's the objective. I want to say when I'm sampling, unlike imitation learning, the things I'm sampling come from my own policy. So I'm trying to choose a policy that gives me trajectories that have highest reward on average. And so the important thing is that data generating distribution is a function of data. We're trying to optimize the data generating distribution. The way we're going to do that is we're going to write this expectation as an integral. We're going to move the gradient inside. We're going to do a little multiply and divide. And we are going to like rewrite this as an expectation of grad log phi times r. I think one thing that will be helpful is to think about this from the perspective of like intuitively what happens, right? So intuitively, what does this objective do? So what this objective is going to do is it's going to say, let's draw a bunch of trajectory samples, okay? And then I'm going to say, let's say this reward was 100, this reward was -10, this reward was 500, this reward was 0, right? What this objective really does is it says, I'm going to increase the likelihood of a particular trajectory proportional to how high the reward was, right? And so I'm going to say, okay, well, r equal to 500 is the best thing, right? So I'm going to like increase its likelihood a lot. R equal to 100 is pretty good, so I'm going to increase its likelihood a lot. R equal to -10 is pretty bad, right? So I don't want to increase its likelihood much. I want to decrease its likelihood. R equal to 0 shouldn't change anything, right? So I'm just going to like leave it as is. So the important thing to think about is it's literally just trial and error. Yeah, you're drawing a bunch of trajectories, and you can think of grad log p as like increasing the likelihood. It's saying like this is the likelihood of the trajectory. You are trying to take the gradient, which means you're trying to increase the likelihood, and you're increasing the likelihood proportional to the reward. So things that have higher reward go up more. Things that have lower reward go up less. Right? And so it's kind of like I always think of reinforcement learning as guess and check. You like throw a bunch of darts, you see which darts got higher scores, you increase the likelihood around things that are higher scores, and then you repeat, right? And so this is called the reinforced trick, but I think I had an example that looks like this, right? So imagine this was like a set of samples that you drew. These things were higher. You're going to try and increase the likelihood of producing those things that are higher reward. And so in imitation learning, you increase the likelihood of expert actions. In reinforcement learning, you're going to draw a bunch of your own samples and then increase the likelihood of things that you drew that were higher reward. Right? But they look very similar as objectives, but they're not. They're not the same. So I think it takes a little bit of time to internalize this. We'll go over this in more. I'll repeat it again on Monday, but just remember the important trick is just this multiply and divide, and this is chain rule. Like that's all there is to the derivation. Multiply and divide and chain rule. Okay? Cool. But I always find it useful to like take the final expression and then it's just think of it as trial and error. It's guess and check. Try a bunch of stuff, increase the likelihood of the good stuff. Okay, I realize we're at time, but I will see you all on Monday. Thanks.